Good morning or afternoon, chemistry students. You get me again. All right, so our learning target today is 5.3. I can explain the process of how an atom can produce different colors of light. And you might not have even thought about how atoms or that atoms can produce light, but you've actually seen it in many different places. You may have seen it at a campfire or a bonfire where someone throws a copper pipe or something else into the fire and it starts to glow green. You've seen it with fireworks. The way we get different colors of fireworks is going to be from the process that we're going to talk about today. You've seen it with neon signs. When you have neon signs, really all you have is a tube full of gas that they're running electricity through, and it gives you different colors. So let's get started. So something we've known since the 1800s is that different elements will give off different colors when you put them in fire. This is what's known as the flame test. We can actually use this to identify different metals. Not all metals are going to do this, but many of them will. And I hope at some point you're able to do this flame test. And like I said, neon signs. So we have different colors of neon signs, and all this is the tube of gas that electricity is running through, and each different color is a different element. Some are actual neon, like that's where they call them neon signs. But it's other gases as well, and that's what we're going to see in class today. So think about we were talking about the prism, and you take white light and you put it through the prism and you split it up into all the different wavelengths. Well, when we're talking about neon lights, we're talking about other colors. Like why does this thing just glow orange? What we're going to start to see is what wavelengths actually make up this. Is it only orange light, like only orange wavelengths, or is there something else going on? So we're going to start by having you guys watch a video about looking at neon lights, or in this case, we're actually going to use helium and hydrogen, and trying to figure out what wavelengths are actually being given off when we look at those different colors. So I'll be back with you after you watch that video.
Chemistry students, here is a very simple tool that had a major impact on what we know about the atom. And granted, it didn't look like this, it wasn't from Flynn, but it's the same idea as a prism. So it's a spectroscope. So what is able to happen is if you look at this end, you point this end at a light source. And you can see there's a little open window here, and then actually you might be able to see there's some lines on there. So what you do is you look through this end. You can see there's a little window in there, and what that does is it takes the light that's coming into the tube and it hits this, it's called a diffraction grating, and it separates it based on the wavelength, separates it just like a prism does, and I'm actually able to see the different colors of light. So the next thing you're going to see is this actually in practice. So here we go. Here is what the setup is going to look like. I have a tube of helium in that plastic tube, or that glass tube, and then I have my spectroscope just set up on a clamp like that. And let's see what it looks like. All right, so I've just turned on the helium light. So as soon as electricity starts to run through that gas, again, the only thing in that tube is gas. It starts to glow this like peach color. And now I've got the spectroscope set up. And when I bring the camera right up to it, you can clearly see how on the left side I have a red, I have an orange, I have a green, and I have two blue. So those are the wavelengths that are making up that peach color. And all right, now I'm going to try a hydrogen tube. So this tube just has hydrogen in it. So it has this purple color. Now I start to look into the spectroscope and there you go. So that is the emission spectra of hydrogen. You can see it's got three. There actually should be a fourth distinct line. We're not quite seeing it. But again, each element has a unique signature of lines in its spectroscope.
So that activity you just watched is actually one that we used to do in class, or we do in class when we're actually in class. But I think you actually probably get the best version of it, because many times when students are looking through the spectroscope, they don't see the lines nearly as well as you just saw them. So that was actually a much better way than you would have experienced it in real life. So what I have on the screen now is an image of different emission spectra. An emission just means emitting is to release, is to send something out. So let's look at the axes here. First on the top, it says 4,000 and then A with a little circle, which is a unit you may have never seen before that actually stands for an angstrom. Ignore that. Think about it as 400 nanometers, because that's really what this is. It's equivalent to 400 nanometers. And then we have 700 nanometers here. The top one is the spectrum of white light coming from the sun. If you were to take that spectroscope and look at the sun, this is the spectrum you would see. We have all the colors and they're running into each other. It's known as a continuous spectrum. Here below it are 4 different elements, and you can notice that they don't give off nearly as many colors. The hydrogen that you just saw in the video, there are the 3 colors we saw in the video, and then there's another one that we couldn't really see. So different elements give off different emission spectra. It's a unique to that element. And we actually still currently use this technique to identify what element is what, because we know we have this bank of all these different spectra, and so we know which one is giving off which set of colors. So what we're going to get into is, well, why do they give off light? So here we go. So this starts with the Bohr model. So Niels Bohr came up with the idea of trying to explain what was going on with the electrons that would allow them to give off light when they in different situations. So his model contains a positive nucleus. I mean, obviously now we know there are neutrons in there, but at the time he actually didn't know that. And he thinks that electrons are organized into levels. Each level has its own energy, and the farther it is from the nucleus, the higher the energy. So if you look at the model that I have, I'll just go here and just ignore the red light here, but we have these different levels, and you notice there's a little N. I think you probably have it in your notes. We use N to denote what the different energy levels are. So the first level is the one that's closest to the nucleus, second, third, fourth, and so on. So here is Bohr's idea that electrons can move between the levels. They kind of have a home base, which is known as their ground level, their lowest level they can be. But if they absorb energy, whether it's in the form of a photon, electricity, or fire, that allows, when the atom absorbs that energy, that allows the electron to jump up to a different energy level. And then when it falls back down, it releases light. So that's the overall idea. Now I'm going to break it down into each of those steps. So let's go with this particular electron. In this model, we have the different energy levels. We have the electron represented by this blue circle with a negative sign, and then the positive nucleus there. So the electron is in the first level. And if you think about what you know about opposite charges, they attract. So this electron is attracted to the proton, and it's just kind of hanging out there. And it's in its ground state, it's stable. Well, let's send a photon of red light at it. So this represents my photon of red light. So we send the photon of red light at it, and what's going to happen is the atom can actually absorb the photon of red light. You'll notice it's gone, and you'll also notice that the electron moved. So the atom can absorb the energy, because remember, light carries energy. It absorbs it, and this electron is moved into what we call its excited state. It has energy. It's like, whoa, whoa, I'm all over the place. And it jumps up to this second energy level. But when electrons are in their excited state, they can't stay there forever. So again, there's a pull here from the nucleus. And so it's kind of resisting this pull. It was able to get away from the attraction from the nucleus, but it can't stay there forever because it's not as stable. Everything's trying to get to its lowest energy state. And so what it's going to do is eventually it is going to fall back down. But by doing that, that energy has to go somewhere. So it releases the energy as a photon of light. Cool. So the electron returns to the ground state by releasing the energy. Energy is emitted as a photon of light. The reason they were the same color is because the jump happened from the first level to the second. It took a certain amount of energy to get from the first to the second. Well, that's the exact same fall that the electron is making. So it would make sense that it would release the exact same amount of energy. So So this is what Bohr think is happening. And we still agree that this is why, or this movement of electrons between levels is why light, or different atoms, emit different amounts of light, or different colors of light, I should say. Okay, so let's change the color of the light. Let's go with purple light. First of all, I want you to think back to the beginning of the week, and how does the purple light compare to the red light, both in wavelength and in energy? Hopefully you're thinking that, okay, wavelength is going to be shorter, and the purple light has more energy. So the shorter the wavelength, the more energy. We send this purple light toward the atom. What do you think is going to happen to the electron when the atom absorbs the purple light? Hopefully you said it jumps up to a higher level, or it jumps up to the excited state, but think about how that's going to compare to the red. Purple has more energy, so if you said it would move up to a higher energy level, you are correct. So higher than where the red was, because there's more energy, so it's able to break even further away, go up to a higher energy level. So, but just like our situation with the excited electron in that second level, this one's not stable. It can't stay there forever. And so what it's going to do is eventually it's going to fall back down to the ground state and releases the same amount of energy. So it was in its excited state, but it can't stay there, falls back down. And again, since that it made that same jump, the same amount of energy is released. And so we see a purple photon of light being released. I could do this with green light. So if we picked something that was in the middle for energy between the red and the purple, it would probably jump somewhere between where the red and the purple jumps, maybe the third level, maybe the fourth level. So this hopefully starts to explain why elements have a different emission spectra. So here's kind of a summary of everything, and I know I have a new graph and I'll explain, or new diagram, and I'll explain what it is. So we have the hydrogen atom. Hydrogen atom has one electron, and that electron can be excited, or the atom can be excited, it can gain energy that causes that electron to jump to different levels. But again, it's not going to be able to stay at that level. So in what I have over here in this diagram on the right are 3 of the transitions that the electron can make. So if the electron had gotten up to the second level, falls back down to the first, that's the least energy transition, it could release a red light. That could be causing this red light to be released. If the electron had jumped up to the third level and then fallen back down, that could release this blue light, because it's a more energetic than the change between 1 and 2, but not as much as our last change. If the electron jumped up to the fourth level and then fell back down, it would release the purple light over here. So I want you to think about, okay, there's a fourth light here. What would my arrow look like to show where this fourth light is coming from? I'm going to bring the pen up here. Hopefully what you're thinking is, okay, well, this light is, if I follow this pattern, red was a small jump, or a small fall, I should say. Blue was a bigger one, purple, and then this one is probably even a bigger one. So maybe it's falling down from that higher level down to the second. More energy is being released, so we have a more energetic photon. So it's a shorter wavelength. All right, so again, the goal today was, can you explain the process by which an atom can produce different colors of light? So I want you to take a little bit of time and kind of sit with this and say, okay, can I do that? First, try to do it without your notes. And if you're not sure, go back, look again at your notes, and make a diagram somewhere. Just try to put it into your own words, or your own sketches, or your own doodles to really bring it home. What we're doing tomorrow is very similar to this. It's the same learning target we're staying with tomorrow. You'll have time and you'll see it in a couple different ways and think about it a couple different ways. And so there's no new ideas coming in tomorrow. We're just going to keep working with this one. So I hope you're having a good day, and we will see you tomorrow. Bye.